Dan Malik. I'm the team lead for Mavric, and today we're going to be talking about the presentation task for URC 2016. First, we'll start off with structure, organization, and management. So Mavric is a team under its parent organization, Make to Innovate, otherwise known as M2I. M2I provides us with lab space, funding, and class credit. As an independent study course, we have to submit weekly reports, submit milestone reports, attend events, participate in a critical design review, and submit a final report. Mavric has three sub-teams: mechanical, electrical, and soil team. Mechanical team is responsible for design, analysis, and manufacturing of anything that's physical on the rover. The electrical team is responsible for programming, circuit design, power systems, communication, and camera systems. And then finally, the soil sample team is responsible for designing the soil sample system and understanding the soil sample science necessary for the soil cache task. Sub-team leads are responsible for guidance and direction in their technical area, as well as keeping track of members' work and progress. Individuals are chosen based on commitment to the team, leadership ability, and technical knowledge. The electronics act as a way to control the mechanical systems of the rover. It is a vital part of our design. As our main controller, we use an STM32 Nucleo F411RE development board. This board was a good choice in design because of the vast number of pins that we have for ADCs, for reading sensors, and PWM for controlling motors and servos. Additionally, the board has a FPU, otherwise known as a floating point unit, which allows us to perform floating point calculations much faster than we normally would. This was useful for many areas, such as setting the duty cycle of PWM lines and soil sample calculations. The code for our rover is written in C. We chose this because it's efficient and allows us to easily interface with the microcontroller. The rover takes in a byte array and then performs error checking and validation, and then processes the information. If the packet is incorrect, it will throw it out and it will look for a new packet of information to be sent. If it's correct, it will go on and process it. We found this to be a very efficient and robust way of sending data to our rover. We utilize a similar method when sending data from the rover back to the base station. The rover sends data from the GPS and sensors back to the base station.
On our base station side, we're just running Python through PyCharm off of just a laptop for right now that we're going to use for competition. It's taking various inputs from various Xbox controllers for a user interface. We're then processing those values, as much processing on the PyCharm as possible, packaging that into a sentence that we send over our RFD 900. So that gets sent serially over to the rover, and the rover then parses that on its side to control what it needs to control.
Hi, my name is Pierre. I am also on the mechanical team. One of the tasks that we had for this semester was improving our wheel system. One of the biggest issues we had was with the design of our rover, and our previous wheels were traction and problems with turning. So one of the main problems we had with the traction was only one side of the wheel was actually making more contact with the surface, therefore reducing our contact surface to the whole entire wheel, which furthermore reduced our traction, our total traction within the wheel. Another big issue with that also was with the turning. The side with the more traction, with the more contact surface, actually cut into the ground, and therefore made it harder for us to turn the rover. So we decided to go with our mountain board wheels for very many reasons. One of the main reasons was it was better priced, reasonably priced. Another reason was better shock absorption than our previous wheel design, and also being deflated, we were able to wrap around the rocks a lot better, which was better for our terrain traversal task for the competition.
We identified the three-mast system of the rover as a problem early this semester. The main problem of the three-mast design was inefficiency of space and weight. The first concept for a replacement involved a complicated bracket system with multiple truss supports to secure the antennas to the main camera mast. While more space efficient than the current mast, it was still using more material than we would have liked and would be a complicated machining process. This concept never made it to SolidWorks. The second concept was a flat plate with circle clamp cutouts along the edges to secure the antennas and mast. This design was much simpler to machine as it could be cut out entirely on a water jet. The design was still not as refined as desired though, and and there was still too much extra material and unnecessary geometry. The third concept was a refinement of the second and involved condensing the flat plate to the bare minimum amount of material needed to support the 2 antennas on the camera mast. The fourth and final concept was a further refinement of the third concept. The communications team changed the type of antenna we were using for video communication and no longer needed a large support, so the design was reduced to support just the RFD 900 antenna. Once the final concept was finalized, we had it manufactured. We then moved on to the testing stage. We tested the antenna range as well as terrain transversal with a new central mast design. We discovered that the max range of our antenna was reduced by 30% while using the central mast. We believe this is due to the close proximity of the antenna to the carbon fiber mast. We also observed our center of gravity move forward and upwards compared to the previous design.
Our science plan is divided into 2 stages, our onboard testing and our at-station testing that will happen later. And the results from both of these will be included in our final soil analysis. So for our onboard testing, we'll be using an aluminum shovel to gather dirt from the required depth, after digging it down of course. And this soil will then be dumped into the science tray, which will contain a cache bag and a separate area that will measure the soil's pH, its temperature, and its moisture. So what happens is a servo inside the rover will activate and it'll open a valve on the cache bag slot, allowing the dirt to be filled into it. And it will also remove the pH sensor from the science area. Now, when the proper amount of dirt has been filled into it, then the servo will activate again and the valve in the cache bag will close, sealing it off for analysis later. And at the same time, the pH sensor will be lowered into the science area, and that will allow it to most accurately measure the pH of the soil. Now, the moisture and the temperature sensors at the same time will be completely covered in this area, allowing them to take proper measurements of the soil as well. Then for our at-station testing, once the rover has been returned, we'll essentially be doing the same experiments on the soil again, measuring the pH, the temperature, and the soil moisture to repeat and confirm the onboard tests. And at the same time, we'll also be doing a visual inspection of the soil, looking at the structure of it, the color of it, the contents of it, the identification of the soil type, to see if this soil lines up with what we know can contain organic life.
The claw for the rover was reworked extensively in the last few months. Our prior design was composed entirely of plastic, and this simply wouldn't do for the competition. Our new design also had a constraint that we would be able to mount a laser diode at the center of its axis of rotation to help align the claw when viewed from the camera system. Most of the design work focused on making something that was simple and would work very reliably with as few moving parts as possible. The design went through a few iterations, with the mounting bracket for the servo assembly being the most difficult part. Due to the necessity of a solid bracket to facilitate the laser diode, the servo shaft would need to be extended and the servo mounted above the bracket. The distance that the servo was mounted above the bracket caused an excessive amount of torque due to the high torque of the servo. And this would require that we redesign the mounting bracket for the servo as a completely 3D printed design that encased the servo, that eliminated any issues caused by torque that would cause inaccuracy. All of the design work for the model was done in SolidWorks before the parts were made, and once we had a design we were happy with, the parts were cut out with a water jet mill and assembled very easily by bolting them together. The only part that was required to be made after the initial assembly was a 3D printed washer. Now, this washer was 3D printed out of ABS plastic due to its dimensions that would not be able to be found in an off-the-shelf washer. The claw design should be able to manipulate nearly every object that is required of it due to its simple design and the full range of movement of the arm that supports it. Should we have any issues, I'm confident that by simply stepping back a little bit and taking a better look at the situation and how the rover would interact with it, we should be able to find a solution to nearly every problem.
One of the larger changes this year was the addition of a new camera system for the Mars rover. We chose 3 cameras that is pretty much off-the-shelf FPV components. These cameras are going to be placed on the mast, the arm, and a hazard camera. One of the cool features about these things is that you can easily see both what you're doing, where you're going, and if there's any obstacles around the rover that we may need to see or move around in the future. One of the other things that is very nice about this new camera system is that we change and do a complete overhaul of the transmission system. We detached from the old 5 GHz Wi-Fi system and moved toward a much more common 1.2 GHz with a much higher output wattage. One of the pluses about this system is that we both have longer range and much better penetration against anything that would really cause some issues with 5 GHz. Communications-wise, on our rover, we have 2 main systems of communicating between the rover and the base station. One is the control system antenna, and one is the video system antenna. The control system uses a 900 MHz antenna, and the video system uses 1.2. These 2 antennas are situated fairly close to the rear of the rover and are easily recognizable to the rest of the rover. Those 2 antennas can communicate to the base station via our base station antenna, which is pretty much the same near replica of the antennas that are on the rover. For our rover right now, we're currently using lithium iron phosphate batteries, or LiFePO4s. These batteries were chosen because they were much more stable and less prone to any overheating issues that you would get from any other batteries such as LiPos. This was very important to us because of the extreme dry and heat environments that you will be facing in both Mars and the Mars Desert Research Center that we will be competing at.